Alright, once again we have another gas law, another equation that will allow us to predict the behavior of gases based on the movement of the particles. Alright, this is Dalton's law. Very often in the lab we wind up dealing with mixtures of gases, and Dalton's law lets us do that in a pretty straightforward way. Remember, kinetic molecular theory says that these particles are ignoring each other anyway. They're not paying any attention to each other, they're not attracting, they're not repelling, at least within the limits of error that we're willing to accept. And so we can just say, oh well, we have gas A banging around in there and pushing against the walls, and we have gas B banging around in the same container and pushing against the walls, and so the total pressure on the walls is just going to be the sum of those two. And of course this could be expanded to as many gases as you like. We could have gas C and gas D and gas E, and it would be fine. You just add them all up and that will give you the total pressure. Mathematically, super simple. In practice, maybe not so much. So let's talk for a second about doing lab work with gases and how we're going to use Dalton's law in that situation. Alright, let's say that we have performed a chemical reaction, one of the products is a gas, and we want to collect it. Instead of just letting those bubbles escape into the atmosphere and be lost, we actually want to trap that gas in a container and hold on to it. Well, there are a couple of ways that we could do that. The first way is called water displacement. And I hope that the phrase water displacement rings some bells for you and makes you think of 8th grade when we found volumes of irregularly shaped solids by water displacement. And maybe even makes you think of Archimedes and making his bath overflow and running dripping wet and naked through the streets of the city yelling, "Eureka, Eureka!" Well, this is not quite the same, but the idea is similar. Here is our reaction vessel, and our reaction vessel is producing bubbles of gas. That gas is what we want to trap. And so we put in it a rubber stopper that has one hole in it. Through that hole we put a little short glass tube. Connected to that little short gas tube is a long rubber tube, which we're going to bring over here to the side like this. Now this is in a pneumatic trough, which is basically a box full of water. Turned upside down over it, we have a gas collecting vessel. Okay, I'm drawing this as a bottle. It might be more of a long test tube called a eudiometer, or a graduated cylinder. We very often use graduated cylinders, or whatever. Here's our water level. Now this bottle was originally also full up to the brim with water. And then we put a lid over it, our thumb or a watch glass or something, turned it upside down. And so the water level dropped a little bit. Gravity pulled some of the water out and into the pneumatic trough. What's left up here? Water vapor. The water has evaporated just a little bit, and so we're going to have a little bit of water vapor left up in here. And that's all. No other gas. Because we didn't leave room for any other gas when we put the top over our bottle and inverted it in the pneumatic trough. There was no other gas present. So there's water vapor up here and nothing else. As our bubbles escape from our reaction vessel and travel down the tube and then travel up through this water and break up here, now we're going to wind up here with a mixture of water vapor and the gas that we're trying to trap. And so here we are directly in a Dalton's law situation. If gas A is the gas that we're trying to collect and gas B is the water vapor, there we go. How are we going to get the measurements that we need, though, in order to do any kind of calculations. We can't stick a barometer up into this gas collection bottle in order to measure the pressure. We can't stick a thermometer up into there. Thermometers are notoriously bad at turning sharp corners, and so we can't get the bulb of a thermometer up there to measure the temperature. What are we going to do? How are we actually going to get the numbers that we need to do any kind of calculations with this mixture of gases? All right, let's think about this for a minute. First of all, the temperature. All right, the temperature may have been quite warm over here if this was an exothermic reaction, or it may have been quite cold over here if it were an endothermic reaction. But by the time it has traveled through here, being exposed to the temperature of the water through the tubing, and then it's directly bubbled through some more water at the same temperature. If it were hot, it's going to cool down as it bubbles through the water. If it were cold, it's going to warm up as it bubbles through the water. And so the temperature, by the time it gets up here, is going to be the same as the water temperature. Well, that's easy peasy. Stick a thermometer into the pneumatic trough, and you've got your temperature. Pressure. All right, we've got two problems here. One is trying to get any kind of a measurement of the pressure that's inside this collection bottle or graduated cylinder it is, or whatever it happens to be, because we can't get a measuring device in there. Well, let's think about this for a minute. We could shove this bottle deeper into the pneumatic trough, right? We could lift this bottle up out of the pneumatic trough. As we do that, the weight of the water is going to exert pressure on the water that's in the bottle. Okay, if we push it deeper, we now have air and water pushing water up into the bottle. If we lift it up to where it's almost out of the water, which is the way we've got it drawn here, just barely under the surface of the water, then we have only air pushing water up into there. So we can change the pressure in our collection bottle by how deep we push the bottle down into the pneumatic trough. Think about this for a minute. If we push this collecting bottle down into the pneumatic trough until the water level inside the bottle is equal to the water level outside the bottle, then the pressure of the gas inside the bottle will be the same as the pressure out in the lab. If it were not, if this pressure were lower, then the atmospheric pressure would push more water in. If it were higher, then the increased pressure in here would push more water out. So if the two water levels are even, then the pressures are even. Oh, all we have to do is measure the pressure in the lab. However, we now have a second problem, because the gas that is up here is not just the gas that we're trying to collect. It's a mixture of the desired gas and water vapor. So now we're going to have to use Dalton's law to figure out what the pressure of the desired gas is. So we have a total pressure that we got by measuring the lab pressure. So now we're going to have to say that the pressure in the lab, the total pressure, is equal to the pressure of the desired gas A plus the pressure of the water vapor. Well, we've measured that. This is what we're looking for. We need a way to get this. Fortunately, how much water evaporates depends on the temperature. And so there are charts saying at this temperature, you're going to have this much water vapor pressure above the water. And at that temperature, you're going to have that much pressure from the water vapor above. And so you've already got your temperature. Look it up, and it will tell you what the pressure of the water vapor is. Subtract that from the lab pressure, and you have the pressure of the desired gas. How nice. All right, what about volume? Well, if you're using a graduated cylinder or a eudiometer, you can just read the volume directly off the collecting vessel. It's going to show you a water level at the 20 milliliter mark and you say, okay, I have 20 milliliters of gas. So you just read this from the collecting bottle. Now, the order that you do these things in is going to make a difference. If you tried to read the volume before you have equalized the water levels, when you equalize the water levels, that's going to change the volume. Oops. You're going to have to be sure that you equalize those water levels before you tried to read the volume. That really, really makes a difference. All right. So now we've got a way to find our temperature, a way to find our pressure, a way to find our volume. And so now you can plug this into the ideal gas law and find out how many moles of gaseous product you produced. Kind of easy peasy in a way, as long as you are aware of these little tricks for getting the values that you need. Now, that's only one of the ways that we could do this, and it's the way that we, by all means, are going to do. There is a second method. Sometimes water vapor is not acceptable. It may be that this gas is going to react with the water vapor, or for some reason you just can't tolerate having water vapor in there with your gas. In that case, you're going to have to use mercury displacement. Not nearly as safe, and so you can bet your booties we're not going to do it. This will be the same basic setup, it's just you put mercury in here instead of water. And mercury doesn't evaporate much under the conditions that we would be working with, and so you can pretty much neglect the fact that you're going to have a mixture of mercury vapor with your desired gas. It will be well beyond the range of your sig figs 99 times out of 100. So you can just neglect the presence of gaseous mercury. But there again, we're not going to do it. Well, how do you know when you read a problem whether it was collected by water displacement or by mercury displacement? Because they can write a problem any way that they like. Look for the phrase over water. If it was collected over water, then it was a water displacement, and you're going to have to worry about doing these corrections for the pressure of the water vapor at that temperature. And if it doesn't say that, or if it says over mercury, then it's a much simpler problem and you don't have to worry about using Dalton's law. All right, let's do an example. Maybe we need another piece of paper here. This, by the way, is not a reaction that you really want to do, but it used to be the way that we made oxygen in the lab all the time. You want some oxygen, you decompose some potassium, it's just no problem. But it tends to go bang sometimes, so we don't do that anymore. All right, so let's go through and see what we've got. We know that, no numbers, atmospheric pressure was 731 torr. All right, remember, we're going to raise and lower our bottle until the water level inside is even with the water level outside, so that our pressure in the bottle will be the same as atmospheric pressure. And so our pressure of our sample is also going to be 731 torr. All right, the water temperature was 20 degrees Celsius, and you have this overwhelming urge to add 273 to it. You don't really have to do that, because the table, we only need this water temperature for the table that tells us how much pressure of water vapor we're going to have. And those tables are generally in degrees Celsius rather than in kelvins. So you really don't have to convert this one. And they are asking us for the pressure of the oxygen. Well, we need one more little nugget of information, and that is the pressure of the water vapor. We're going to have to look that up in a table, and I believe there's one in your book, and find that at this temperature, 17.5 torr of that total pressure is going to be due to the water vapor. All right. So Dalton's law then tells us that our total pressure is going to be the pressure of the oxygen plus the pressure of the water Our total pressure is 731. That's the pressure of our oxygen plus 17.5. Okay, and so when you subtract, you'll find that the pressure of the oxygen is what? 713.5. Now think about sig figs for a minute. Why am I claiming 4 sig figs here when I had 4 sig figs here, right enough, but only had 3 sig figs here, and the table only gave me 3 sig figs over here? How can I do that? Well, I was sloppy. I wrote down 731 instead of 731.0. Shame on me. But notice that all we're doing is adding and subtracting. And so that means it has to do not with the number of sig figs, but with the place value. This is uncertain in the tenths place. This is uncertain in the tenths place. My answer will be uncertain in the tenths place, regardless of how many sig figs that amounts to. And of course, once I've got this pressure, I could then do calculations using the ideal gas law and figure out how many moles of oxygen I had collected. I could do all kinds of other things. But this is the only tricky part. All right, so far so good. We can do this.